Hi everybody, our group is the number 2 and it's composed by Maria Gaya, Ivan Luque and me, Albert Rocco. We've decided to explain the practice number 5, analyzing an asynchronous 4-bit counter using toggle flip-flops. The symbol of one toggle flip-flop is this one. As we can see, we have 3 inputs and 1 output. Here we have the truth table of the toggle flip-flop, and a toggle flip-flop, it can be used to store, save, write 1 bit of information as a frequency divider by 2, or as a pulse to a square wave converter. On the other hand, to develop the 4-binary counter, we have to combine 4 of these toggle flip-flops. The symbol for whole system is this one. As we can see, we have 2 inputs, the clear direct and the clock, and we have 4 outputs. Each one corresponds to 1 bit, and all of these form the value of the state. Here on the right side we can see a table with the values of the outputs in binary and the corresponding state in decimal. As we can see, there are 16 different states, so the system is able to count from 15 to 0. As we can see here, analyzing the symbol, the system doesn't have reversibility and neither counting able. This is because when the clear direct is equal to 1, the initial states corresponds to the S0 and the outputs are 0, 0, 0, 0. But to change the state, we have the clock. With the raising edge of the clock, we can decrease the state. Here we have the state diagram. As I said, when the clear direct is equal to 1, the value of the output is S0, that corresponds to the 0, 0, 0. So the 0 state is the initial state. And then with the raising edge of the clock, decrease the state to S15, S14, state 13, and continues to the initial state. To finish the specifications, here you can see the timing diagram of the system. As we can see, with the raising edge of the clock, we have a change in the output. When the clear direct is equal to 1, we have the initial state 0, 0, 0, 0, that is this state. Before the clear direct, the state is unknown, and then it's what I said. With the raising edge of each clock, we have to change the value of the output. Here corresponds to a 15. The state, and then the states are decreasing since to arrive to 0 again.
For a better understanding of P5 project, I have decided to set the planning in 4 sections. On the first one, second one, and third one, we will talk about the synchronous large, the flip-flop, the JK flip-flop, and the T flip-flop, which are the main parts of the project. To finish, I will explain a little bit how a synchronous 4-bit counter using T flip-flop is going to work. First of all, larges are secret elements built from logical gates whose output depends always on the inputs. As we can see on the logic diagram, the SR large, the inputs are combined with the output of both of the logical gates. And the block diagram explains you that when the input changes, the excitation variable Y changes. On larges, it takes additional delay for the secondary variables to assume the value. Also, the flip-flop is a controlled, stable large where the clock signal is the control signal built from the larges, whose output depends on the input. That means that when the clock changes, the input changes, the output changes. On larges, we have to check every time if the input changes, then change the output. JK flip-flops is basically gated as a flip-flop with additional of a clock input circuit. Due to this additional clock, JK flip-flop has four possible combinations: logic 1, logic 0, no change, and toggle. But in this project, it is important to understand T flip-flop. T flip-flop is a modified form from JK flip-flop, making it operate in toggle region always. Whenever the clock is in low signal, the input is never going to affect. That means that we keep always the previous value given. So when, in another hand, the signal gets high, the inputs get activated and toggles. The synchronous 4-bit counter using T flip-flop, we are going to apply 4 T flip-flops in this case. It is a good practice because the toggle feature is naturally suited for implementation of the counting operation. Also, when T is held high, the toggle flip-flop divides the clock frequency by 2. That means that we are going to divide by 2 4 times our clock signal entrance.
Hi, my name is Ivan, and I'm going to explain the asynchronous counter. Well, the asynchronous counter is composed of one component, the T flip-flop, which we use 4 times. Well, the first one is for the first bit, which is the less important, the next one for the second, the next one for the third, and the last one for the fourth, which is the most important bit. Okay. Now I will explain the T flip-flop a bit. Well, we use the T flip-flop as a clock, a CD, a T, and a Q. Okay. Only works when the clock is on the rising edge. To change, we will only change the state when the clock is on the rising edge, and the T is on 1 because when it's on 0, it not change, we maintain the same state. And if we click the CD and the clock is on the rising edge, also we will reset the state and will be at 0 always. Then, as we see here, when T is 1, we are always changing the next state because it's what a T flip-flop does. And in our case, we always put the T on 1 because we want to make it always changing to be able to count. As we can see here, we put it all in one to be able to count well. Now I will show you how the T flip-flop is on its side. As we can see, it has a D flip-flop and a MUX connected on the T and its previous state to make it work. Now I will show the simulation to see how this works. We didn't represent the T because it's always 1, then it doesn't matter because it would never change. As we see here, we have a value from before, which is 11. And when we arrive to the CD starts, and we arrive to the CD, now the next state is 0 because CD resets the counting. Until we haven't finished to have the CD active, we want to start to count. And as we said, we start from 0, but we are counting from 15 to 0. Then if we were on 0, we pass to 15. As we can see here, every clock period, we are moving. We are moving one number, one clock period, another clock period, another, and we are moving one step down every time. And that's it. This is how it works, the asynchronous counter. I hope it was useful. Bye.